Hello everyone from Math 2200, Discrete Mathematics. Professor Wenson here again with a video on your Zybooks, section 10.12. This is the final section of chapter 10, Counting Problem Examples. So this is kind of putting it all together. In sections 10.1 through 10.11, you were introduced to a lot of different rules for counting in different scenarios. And in 10.12 here, you're just using them all in some way or another. You might have to combine certain, use multiple rules throughout certain problems. But yeah, you just got to know what scenario you're in and what particular counting method of counting applies. So you're saying here, right, counting problems may require multiple counting techniques in combination. For example, Cheryl goes to the bakery to buy a dozen donuts. The bakery sells 5 varieties of donuts: plain, chocolate, jelly, maple, and custard. The bakery has a large selection of plain, chocolate, and custard donuts. However, the bakery only has 3 jelly and 5 maple donuts left. How many different selections are possible for the dozen donuts? Alright, so I'll walk you through this here, play this animation, and then we'll get to other examples after this, of course. Now, the number of ways to select 12 donuts from 5 varieties, and then, with certain restrictions, right? With at most 3 jelly and at most 5 maple. Now, see, the first rule they're applying here is the complement rule. Take the total number of ways to select the donuts without restrictions, and then subtract the opposite of this, the number of ways to select the donuts with, not at most 3 jelly and at most 5 maple. Now, what's the opposite of at most 3 jelly and at most 5 maple? That would be, the opposite of at most 3 jelly, or the opposite of at most 5 maple using De Morgan's law. Now, the negation of less than or equal to 3 is greater than or equal to 3, right? Greater than or equal to 4, greater than 3, which is, for integers, greater than or equal to 4, and the opposite of less than or equal to 5 maple would be greater than or equal to 6 maple. Right. And then here, there is an OR statement, a union. So you could count the number of ways to select more than 4 jelly, or at least 4 jelly, or the number of ways to select at least 6 maple, and then subtract the way to do both, right, using the inclusion-exclusion principle from the last section. So minus, and then see they're taking this here and doing the inclusion-exclusion principle from the last section. Right, and then they actually start putting in some numbers here. The number of ways to select 12 donuts from 5 varieties with no restrictions. Remember, you'd be making these bit strings with 12 zeros and 4 ones, right, to separate the 5 varieties. So that'd be 16 choose 4 minus, and all these, if at least 4 of them have to be jelly, then I'm just doing 8 donuts with 5 varieties. So this would be 12 choose 4. This is I take at least 6 maple, so I only have 6 left to choose from with the 5 varieties. So this would be 10 choose 4, and then minus, if I had to have at least 4 jelly and at least 6 maple, that's 10 donuts selected already, and then I'd have 2 donuts left with the 5 varieties. That'd be 6 choose 4, and putting all that stuff in, and we get our numbers. So again, they're just kind of going, this was back in section, I think, 10.10, maybe 10.9. So putting it all together, you know, 1,130. So based on the restrictions, there'd be only, there'd be 1,130 different ways she could select a dozen donuts from these 5 varieties, when they only had 3 jelly left and 5 maple left in the store. So again, this is just one example, but you see how multiple laws were used. Complement law, De Morgan's law, inclusion, exclusion, and then that, selecting n indistinguishable balls from m distinguishable bins, right? Or placing n indistinguishable balls into m distinguishable bins. All those things were used in this one problem. Okay. Alright, so I'll let you read through this example on your own. Let's get to this next activity. Alright, so a manager of a grocery store purchases 50 crates of soda to stock the store. There are 5 varieties of soda. How many ways are there for her to purchase the 50 crates of soda if she does not order more than 25 of any particular variety? Alright, so let me write this stuff down. So 50 crates of soda she's ordering. And there are, 5 varieties of soda. So if there were no restrictions, right? If there were no restrictions, we'd be talking about solving this kind of an equation where, the number of crates of the first variety plus the number of crates of the second variety plus the number of crates of the third variety plus the number of crates of the fourth variety plus the number of crates of the fifth variety. Those numbers have to add up to the, the 50 crates she's purchasing. And each one of these can be, 0 up to 50. Right? If there were no restrictions, each one of these could be anywhere from 0 up to 50 as long as they add up to 50. So remember, the number of ways this could be done, the number of ways she could order 50 crates from these 5 varieties with no restrictions, well, there'd be, the number of ways this could be done would form a bijection with these, remember those code words with the bit strings where there'd be 50 ones and 50 zeros and 4 ones to separate the 5 varieties. So it'd be 54, choose 4, or 54, choose 50. Either way. Alright, so that's with no restrictions. But they did give us some restrictions. Right, the question is, how many ways are there for her to purchase the 50 crates of soda if she does not order more than 25 of any particular variety? So x sub I, so here are the restrictions. So x sub I is less than or equal to 25, for I equals 1 to 5. Right, so the number she orders is at most 25. So it's kind of like the earlier problem with the donuts. There were some varieties she could only order, like here it was, she could only get at most 3 jelly and at most 5 maple. It's kind of similar to that. So if I want to count the number of ways to order with, at most 25 of each variety, so at most 25 of the first variety, and if you wanted to write this out this way, this would be at most, you know what, I'm just going to say x1 is less than or equal to 25, and x2 is less than or equal to 25, and x3 is less than or equal to 25, and x4 is less than or equal to 25, right? And x5 is less than or equal to 25. Right? Sorry, that's pretty long there. We could figure out. I would say I would like to do this by complement instead. So this would be equal to the number of ways without restrictions, right? The total number of possible ways to order the 50 crates minus, and then the number of ways to order these 50 crates that's the opposite of this. All right. Do the complement. Now the complement would be that you order 26 or more of the first, or 26 or more of the second, or 26 or more of the fifth. Right? Again, this would all be connected by or, so a big union here. Right? Big union. Now, this is a little trickier. All these sets are mutually disjoint. They cannot, two of these cannot happen at the same time in this union, right? Because if I ordered 26 or more of the first variety and 26 or more of the second variety, that'd be 52 crates or more. But I'm only ordering 50 crates. So these are mutually disjoint. So I can just apply the sum rule. So this is going to be the number of ways with no restrictions minus, and then applying the inclusion-exclusion principle. But again, because all these 5 events, all these 5 sets are mutually disjoint, I just have the number of ways to order at least 26 of each variety, right? Plus the number of ways that x2 be greater or equal to 26, and these are really all the same thing. Plus the number of ways that x5 could be greater or equal to 26. But really, I just need to find one of these and multiply it by 5. Because each of these, it doesn't, these variety, it doesn't matter. All these will give me the same number. All right, so let's talk about this. What if I give just, what if I have to take 26, at least 26 of x1? Well, then there'd be 24 left for these 5 varieties. If I give 26 to x1, order 26 x1s, then there'd be 24 left for the 5 varieties. So 24 zeros, 4 ones. That'd be 28. Choose 4. And again, times 5, right? Each of these would be the same. Right? Because again, if I give 26 to x2, it would be the same. It would be the same problem. And this I found earlier. The number of ways to do it with no restrictions at all would be 54. Choose 4. And then I subtract 28, choose 4 times 5. And again, this is applying the complement rule, the sum rule. The again, number of ways to put indistinguishable balls into distinguishable bins. Right, lots of things going on here. So back here, they do ask us, how many ways with no restrictions? 54, choose 4. And then again, what is x here if I'm using the complement rule? This is the number of ways to purchase soda with at least 25 of some variety chosen. Right. Well, not at least 25, right? At least 26. The opposite of at most 25 is at least 26. Of some variety, not every variety, because you can't have at least 26 of every variety. You're only ordering 50 crates. So let VI be the set of ways to choose 50 crates from soda, right? 5 varieties with at least 26 crates in that variety. What is the correct expression, right? We're counting the union of those, which would be, again, 5 times 28, choose 4. Right? All the intersections have nothing in them, because again, you can't have more than one variety, have 26 or more crates. And what is the union then? The size of that union, 5 times 28, choose 4, and then counting the number of ways, you get 54, choose 4, minus 5 times 28, choose 4. That was this number here. So 213,876 different possibilities. All right, if I am going to, there are 213,876 different ways she could order the 50 crates if she wasn't going to order more than 25 of any particular variety of soda. All right, and then again, that's just one example, and you can read through this one, look at this one again, look back through the sections, 10.1 through 10.11, because all those are coming back. And so, now there's tons of exercises in this section. Look at this. 10. There are 25 problems with multiple parts. Again, because it's putting all of chapter 10 together. You are applying some rule, multiple rules for some of these problems. Maybe just one rule, multiple rules. It depends on the problem, depends on the scenario. So please, I would highly recommend looking at all of them. I know I didn't assign all of them, but I would highly recommend still trying and looking at all of them. Practicing all of them, getting more exposure, better at the material, hopefully, with practice. And of course you can check the solution when you're done and see if you got it right or not. But do check the solution after you've worked on it though. Right? Don't just look at the solution right away and copy it and think you've learned anything. Right? If you didn't try, you're not going to learn anything. All right. So again, I'm just going to show you the one example. I went over the animation. Again, not every problem is like those examples. I'm not going to do every single possible kind of problem here. You saw how many there are. Just saying that this kind of puts all of chapter 10 together. All right. You're going to see, as you work through all these exercises, you're going to see every rule at least once probably showing up here. Okay. All right. Yeah, that's all I got for you. All right, just practice, practice, practice. And if you have any questions, of course, send them my way, send me a message. And thank you very much for watching.